Welcome to The Explainer. Today, we're digging into the surprisingly simple but incredibly powerful idea behind things like ChatGPT. It's all about something called an autoaggressive model. And trust me, by the end of this, you're going to get exactly how it works. So, let's just dive right into the big question, right? How can a machine be creative? How does it actually generate a complex picture or write a story from a blank slate? Is it, some kind of magical spark of inspiration? Well, not quite. The secret sauce here is a mathematical idea called the chain rule of probability. Now, don't let the mathy name scare you off. The concept itself is super simple. Think of it like building with Legos. You don't try to build the entire castle all at once. Nope. You just focus on one thing. What's the very next brick to add based on all the bricks you've already put down? What this does is pretty brilliant, actually. It takes this giant, overwhelming problem, like creating an entire image, and breaks it down into this series of tiny, bite-sized steps. The model doesn't need to see the whole masterpiece at once. It just has to figure out, okay, what comes next? To really see this recipe in action, let's look at a classic AI challenge, getting a machine to draw a handwritten number. We're talking about those famous MNIST digits. Each one is a tiny 28 by 28 pixel grid. That's 784 individual pixels the AI has to place, one by one. So the first crack at this was, well, pretty basic. For each and every one of those 784 pixels, they used a simple statistical tool. The model would just look at all the pixels that came before it, going from top left to bottom right, and make a simple guess. Should this next pixel be black or should it be white? And the results? Yeah, they were blobs. Just total, unrecognizable, blurry messes. It was pretty obvious that this simple model just wasn't powerful enough. It couldn't see the complex shapes in the numbers. It was kind of like trying to paint the Mona Lisa with a paint roller. Just not the right tool for the job. So clearly, the model needed a major upgrade. It needed a smarter brain to handle all that complexity. And that upgrade came in the form of a neural network. A neural network is way more flexible. It's designed to find and learn those complicated, twisty patterns that the simpler model just couldn't see at all. It basically gave our system a much, much more sophisticated brain. Okay, but here's the catch. This new, powerful brain came with a big problem. If you used a separate neural network for every single one of those 784 pixels, can you imagine? That's like hiring a whole army of experts just to draw one number. It was way too slow, way too inefficient. It just wasn't going to work. And then someone had a really clever idea, a breakthrough called weight tying. The concept is just genius in its simplicity. Instead of training 784 different models, what if you just train one really good model, and then you just reuse it? You share its knowledge, its weights for every single prediction. It's like creating one master pixel predicting expert and having it do all the work. And the difference this made was just massive. The number of things the model had to learn, the parameters, went from growing exponentially n squared to just growing linearly with the number of pixels. Basically, it made the whole thing way more efficient and actually possible to train in a reasonable amount of time. So with this smarter, more efficient brain in place, the results got so much better. Look at that. The model could finally generate things that actually looked like handwritten digits. Yeah, they're still a little fuzzy, a little ghosty, but the structure is there. The upgrade totally worked. Okay, so this works for pixels, but what happens when we take this exact same idea, predicting one piece at a time, and apply it to something completely different, like language? For this job, researchers turned to a special kind of neural network called a recurrent neural network, or an RNN. Now, what's cool about an RNN is that it has a kind of memory. As it goes through a sequence of text, it keeps a running summary of everything it's already seen, and it uses that memory, that context, to make a really good guess about what the very next character should be. So they took this RNN and fed it all the works of Shakespeare, and what came out was kind of amazing. Just think about it. It's only predicting one character at a time, and yet it learned English grammar, it learned punctuation, it even picked up on Shakespeare's unique style. Sure, it makes up some words here and there, but the structure, the feel, it's undeniably there. Then they did the same thing with Wikipedia, and it started spitting out these completely made up but perfectly structured encyclopedia articles. And what's really wild is that it even learned Wikipedia's specific formatting for links, remembering to open and close the brackets correctly over these long, complex sentences, all just from predicting the next character. All right, let's zoom out. What's the big picture here?
Why does this one simple idea of step-by-step prediction matter so much?
The main thing to remember is this. Whether you're drawing a number, writing like Shakespeare, or generating fake history, the core process is exactly the same. You break a huge, complex creation down into a simple series of what's next predictions. It's an incredibly powerful and flexible recipe for getting an AI to create things. This powerful prediction engine, this simple idea of just figuring out the next piece of the puzzle one step at a time, that's the fundamental engine driving so much of the AI revolution we see today. And it leaves us with one pretty mind-bending question to chew on.